This is the video for Module 12, Section 7.3, about adding and subtracting rational expressions with the same denominator. If we look at two fractions or two rational expressions that have the same denominator, if we want to add or subtract them, we can just do this by adding or subtracting their numerators. When we do that, the denominator for our resulting expression is going to be the same as the original common denominator. Here are some examples. First, let's look at an example where we're just dealing with fractions. So if we're taking 8/7 and subtracting 3/7, notice that these two do have the same denominator, so we can just go ahead and do the subtraction. And the way we do that is just subtract the numerators, and our new denominator is the same as the common denominator that we had between the two original fractions. So our denominator for our result is going to be 7. And then on the top, we just subtract the two numerators. So we end up with an answer of 4/7. Now let's look at what happens with a rational expression. It's the same idea here. If we already have the same denominator or a common denominator for both of the rational expressions, then we can add or subtract these just by adding or subtracting the numerators. So in this case, we're adding our numerators, which are 3 and 4. And we're writing this now as one rational expression, and our denominator is going to be the same denominator that we had in our original two rational expressions. So we'll end up here with a result of 7/12x. Let's do some more examples. We're just going to add or subtract each of these, and then we'll simplify the result if we can. So the first thing to do is to check and make sure that the denominators are the same. We have a 4 in both places here. That means our new denominator will be just the same as those two. So we know our denominator will be a 4. Now for the numerator of this, we're going to take the two numerators we have, and since this is a subtraction here, we're going to subtract them. So I'm going to write both of these in parentheses so that we don't forget to apply the negative to both terms of our second numerator. So what we end up with here is our first numerator, which was 8a plus 2b, and then we're applying the negative to each one of these, and that means we'll have a minus 8a, and then here we have minus a negative 2b, so that will end up being plus 2b. That's still all over 4. Now all we have to do in our numerator is combine like terms. So we have the 8a here and the negative 8a, and those will cancel each other out. And then we have a plus 2b here and another plus 2b. So we will end up with 4b in our numerator and 4 in our denominator. Now notice up here in the directions, it asks us to simplify the result if possible. That means we're going to be using what we talked about in the last section and looking for any factors that we can cancel. Since both of these have a 4, we can go ahead and cancel that. And that means we just end up with a final result of b. Let's look at the next example. Again, our denominators are the same. So we can go ahead and write that common denominator as the denominator of our new rational expression. And for our numerator, we're going to take the two numerators we had and add them, since our operation here was addition. So we end up with 7y squared plus a negative 7y. Now we can't do any combining of terms here since these aren't like terms, but notice that we can do some factoring. Since both of these have a 7y, we can factor that out, and that leaves us with y in from the first term and a negative 1 from the second term. And if you notice, this y minus 1 in the denominator counts as a factor because it is the whole denominator. So we can cancel that with the y minus 1 in the numerator. And our final simplified answer is just 7y. One more down here. Again, our denominator is the same for both of these expressions. It's m minus 3. So that's our denominator for our new expression. And on the top we have m squared minus 7m. Our operation in between was a plus, so that gives us a plus 12. Now we've done the addition. Again, we need to simplify, which means we need to factor our numerator if possible. Since this is a trinomial, we can try factoring it into two binomials. Since we just have an m squared here, then we'd have an m as our first term in each binomial. Since our first sign is a minus here, we can put a minus there. And since our second sign is a plus, that means that these two signs have to be the same. So that means that this one has to be a minus also. So now we're looking for two numbers that multiply to 12 and add up to 7. So that would be 3 and 4. Because 3 times 4 is equal to 12 and 3 plus 4 is equal to 7. So, and again, we're going to put the bigger of the two in our first binomial, so we'll have m minus 4 times m minus 3. Now again, our denominator, if we look at the whole thing, that counts as a factor, so we can cancel it with the m minus 3 we have on the top. And that leaves us with a final result, simplified, of m minus 4. The next thing we're going to talk about is finding the least common denominator for a list of rational expressions. This is something that we'll use in the next section when we're adding or subtracting rational expressions that don't have the same denominator. So our first step is going to be to factor each of the denominators. And then what we'll do is that for each different factor that occurs, we'll find the maximum number of times it does occur in any one denominator. So first we'll do this with fractions, where we only have numbers to think about. And then we'll try and connect that and see how that works the same with rational expressions. So if we're trying to find the least common denominator for 1/18 and 5/8, then we'll start by looking at our prime factorizations. So the prime factorization for 18 well, we can write 18 as 9 times 2. 9 we can break down a little bit further into 3 times 3. So this would be the same as 3 squared times 2. The other denominator is 8. So if we write the prime factorization of that, we would end up with 2 times 2 times 2, or 2 cubed. So now the two different factors that we have here are 2 and 3. And the other thing we're looking for is the maximum number of times that that factor occurs. So if we look at the 2, it occurs once in our first denominator. It occurs 3 times in our second denominator. So the maximum number of times it occurs in any one place is the 3 times. So we're going to say here it occurs 3 times. And for the 3, it occurs twice in our first denominator, not at all in our second denominator. So the maximum number of times it occurs is twice. So we'll take these two things, and that means that our least common denominator will have this as our base and this as our exponent. So we'll have 2 cubed times 3 squared. And if we multiply that out, that's going to be 8 times 9, which is 72. So our LCD for these two fractions would be 72. Now let's look at how this would work if we have some variables in there as well. And remember, we're not looking at the numerators here at all, only at the denominators. And here we don't have any factoring to do, and even our numbers are already broken down as far as they can be. So we're just looking at our different factors. So the different factors we have are 3, 5, and x. maximum number of times for each one. For the 3, we only see it once in this one rational expression. The same with the 5, it only occurs once. And the x, what we're looking for here is an exponent. The highest exponent we have here is the 5. So the maximum number of times that one occurs is 5 times. So again, the factors are going to be our bases, and the number of times they occur will be our exponents. And that means that for our LCD, we'll have 3 to the first power, although we don't have to write the 1 in there. And we'll have 5, which occurs once, so we have 5 to the first, and then we have x to the 5th. And if we multiply all that out, if we multiply the 3 and the 5 together, we end up with 15 x to the 5th. Okay, so let's look at a list of rational expressions and see if we can find the least common denominator for all of the expressions in the list. So again, we're only looking at denominators here. We're not paying any attention whatsoever to the numerators. And remember that as we have in these two rational expressions, if we have something like x plus 3 and that's our whole denominator, that counts as being a factor. So if this helps, you can even put the whole denominator in parentheses, and that tells you that you have two different factors there. So our factors are x plus 3 and x plus 5. The maximum number of times each one occurs is just once, because this one only occurs in this rational expression and it only occurs the one time, and the same for the x plus 5. So that means our LCD will just look like this. We'll have x plus 3 to the first power and x plus 5 to the first power. And that's all there is to it. So our LCD would just be the product of those two factors. Okay, for our second example, we are going to have to do a little bit of factoring here. So we'll start out by factoring each one of these denominators. For this first one, there's a common factor of 3. So if we just factor that out of both of these terms, then we have 3 times a plus 9. For our second one, both of these terms have an a. So if we factor out the a, then we have an a plus 9 remaining. So to find our LCD now, we're going to write down each different factor that we see in any of the denominators. So we have a 3 here, and again that counts as a factor because it's multiplied by this other factor. Another factor that we see in this first denominator is the a plus 9. And then in the second denominator we have an a also, and that counts as a factor again because it's multiplied. There's no addition or subtraction along with it. And we have the a plus 9 again. We don't have to write down the a plus 9 again though, because we already have it written down as one of our factors. So now we're looking at the number of times each one of these factors occurs. The 3 only occurs once. And the a plus 9, even though it occurs in both of our different denominators, the maximum number of times it occurs in any one of them is only once. So we only need to put that down as a 1. And the a only occurs once in this one denominator. So that means our LCD is just going to be the product of these 3. So it's actually going to be 3 times a plus 9 times a, and we can write it in a little bit nicer looking form just by writing it as 3a times the quantity a plus 9. Alright, for this example, again we want to do any factoring in the denominators, and there's not really any factoring to be done here, but if you notice, we've talked a lot about opposites, and if you notice the 3 minus x and the x minus 3 are actually opposites of each other. So that means that we could rewrite the 3 minus x as negative 1 times x minus 3. If we do that, then now by doing that, we see that we have a factor of x minus 3 in this denominator. And the -1, we don't really need to consider that as a factor. We could actually move that up to our numerator. So we could make this -x, and then that wouldn't even be in the denominator at all. So really in this case we're changing our whole rational expression. Instead of x over 3 minus x, now it's going to be -x over x minus 3. So that means the only factor we have in either of these two is x minus 3, and the maximum number of times it occurs in any one place is just once. So that means that our LCD is just x minus 3. Okay, last example. If we look at this first denominator, we can factor a 4 out of these two terms. So that leaves us with x minus 2. In our second denominator, since we have a trinomial, I'm going to factor this into two binomials. Since we have an x squared here, then we're going to have x and x. We're going to copy this sign down into this first binomial. Since the second sign is a plus, that means that these two have to be the same, so they both have to be minuses. And now we're looking for two numbers that multiply to 4 and add to 4. Well, the only factors of 4 are either 4 times 1 or 2 times 2, and since 4 plus 1 is 5, that one doesn't work, so it's going to have to be 2 and 2. So we end up with x minus 2 times x minus 2. Okay, so now that we've got everything factored, let's write down the different factors we have. So from the first rational expression, we have a 4 as one of our factors and x minus 2 as the other factor. And the only factors we have in the second denominator are x minus 2. So we don't need to write the x minus 2 down again. But now when we get to this part, if we're looking at the maximum number of times that the factor occurs, the 4 only occurs once, but if you look at our second denominator, the x minus 2 occurs twice here. It's actually that quantity squared. So that means here that we would say that the maximum number of times that occurred in any one denominator was twice. And that means for our LCD, we're going to have 4 to the first power times x minus 2, the quantity, to the second power. Another thing we'll need to be able to do is to write equivalent rational expressions. In other words, we want to be able to change any rational expression into an equivalent form. And the way we do that is that we actually multiply by 1. Now 1 has a lot of different forms. In fact, if we have a rational expression where the numerator and the denominator are the same, that's equivalent to 1. So looking at this part right here, the r over the r is the same as 1. So when we're doing this, when we're multiplying p over q by r over r, we're actually multiplying by 1, and that's why this gives us an equivalent expression. So that means that the p over q and the pr over the qr are equivalent. Now what if we start with an expression and we want an expression equivalent to that with a different denominator? So let's look at an example where we're starting with 3 over 8m and we want to write an equivalent expression, but we want the denominator of our expression to be 8m times the quantity m plus 6. Let's write it out this way. So we're starting with 3 over 8m and we want to do something to this so that we end up with a denominator of 8m times m plus 6. Now if you compare the two denominators, the only difference is that the second one also has an additional factor of m plus 6. Well, to get that, we could have multiplied our denominator by m plus 6. So let's write that in here. But now in order for this to be an equivalent expression, we have to be multiplying on this by the same thing on the top as we are on the bottom. So that means that we're really multiplying by m plus 6 over m plus 6. So the idea here is to identify what's missing or what additional factors have been put into the denominator that you want, and then multiply both the numerator and denominator by those factors to get your equivalent expression. And so notice when we actually multiply this, in our new numerator, we'll have 3 times the quantity m plus 6. Notice how this looks a lot like our formula up here. We have our original rational expression, the p over q, in this case was the 3 over 8m, and then we're multiplying by the same factor on the top and the bottom, which in this up here was the r. In this one it's the m plus 6. Now we could leave this one in this form. In some places in your homework it's going to ask you to multiply these out, which means you have to distribute. Up here you'd have to distribute the 3 to both of these terms. Down here you'd have to distribute the 8m to both of these terms. So if we did that here, we'd have 3m plus 18 over 8m squared plus 48m. Now whether you need to do that or not just depends on the problem. You'll have to read the directions in the problem to tell whether to multiply these out or to leave them in factored form. Okay, let's do a couple more of these problems. And in these, they're telling you what the new denominator needs to look like. The thing that's going to be the most helpful in a problem like this is to factor your denominator. If you can see that it can be factored, for example here both of these have a factor of 5. So if we factor this as 5 times x plus 4, then you can see what factor has been added in here that makes it different than the original denominator. So the only difference between these two is that this has an additional factor of 5. And that means to get this denominator, we need to multiply both the numerator and the denominator here by 5. So we're going to take our original rational expression times 5 over 5. That will make our new denominator this. That will give us a new numerator of 5 times x. And our denominator will be 5 times the x plus 4. If you want to make it look exactly like this one, then you could go ahead and distribute that 5 again. So you'd have 5x plus 20. So here's our equivalent expression. Okay, in this problem, again, if you look at the second denominator, we can do some factoring there, because otherwise it's not very easy to tell what factor has been multiplied in here. And if you notice, since 9 is the same as 3 squared, we actually have the difference of squares here. So we could factor this as a plus 3b times a minus 3b. Now we can see that the new factor that's been multiplied in here is a minus 3b. So we're going to take our original rational expression and we're multiplying by a minus 3b over a minus 3b. Just remember that you can do anything you like to the denominator as far as multiplying, as long as you're multiplying the numerator by that same factor. So now on the top we have a times the quantity a minus 3b. In our numerator we have a plus 3b times a minus 3b. And let's go ahead and distribute the a in the numerator, so that gives us a squared minus 3ab. And in the denominator, a plus 3b times a minus 3b should give us the original denominator we started with here that we factored. It would be a good thing to go ahead and multiply this out and check. That would be a good way to check our factoring. If we do that, we're going to end up with a squared minus 9b squared, which was the denominator that we wanted. Okay, one more problem. Now in this one, the denominator that we're looking for is already in factored form, but our original denominator isn't. So let's factor our original denominator and see what we end up with. All three of these have an x, so let's start by factoring out x. That gives us x squared plus 2x minus 3. And now we have a trinomial, so let's try factoring that into two binomials. So we'd have an x here and an x here. We carry this sign down here, so that's a plus. Since our second sign is a minus, that means these two signs have to be different, so that makes this a minus. We're looking for two numbers that multiply to give us 3 and subtract to give us 2. And again, the reason that we're subtracting here instead of adding is because this last sign was a minus, because these two signs are different. Well, the only two numbers that we can multiply to get 3 are 3 and 1, and if we subtract those two, we get 2. So those are the ones that will work. And again, if we're using this method, you can just take the larger of these two numbers and put it in your first binomial, and that will make your sign here turn out correctly. So now that we've got this all factored, we can compare this to our new denominator, and the only factor here that's missing is the x plus 5, because we already have the x and the x minus 1 and the x plus 3. So that means we're going to take our original rational expression. Let's write the denominator factored though. And we're multiplying by x plus 5 over x plus 5. So if we multiply our numerators, that gives us negative 25 times x plus 5. And for our denominators, we have all four of these factors. And notice that we do have the same four factors, even though they're written in a different order, but that still gives us the same denominator. Since these are all multiplications, we can write them in any order that we choose to. And let's leave this one in factored form, since our denominator here was in factored form. So this would be our final answer. That's the end of section 7.3. So now you can go to MyMathLab and work on your homework for this section.